Okay, we're still in section 1.1. We're looking at field axioms. Now, the whole idea here is just to kind of get us used to some finite fields, and in particular, a lot of these modulus type things. So they talk about Z P, where P is prime. Okay, and the reason for that is that we get a field. Now, a field you know really, really well is the real numbers. And so these field axioms, as you look at them, they're just properties that the real numbers have. And so when we look at something like ZP, just to give you an idea there, most of this is pretty straightforward. It's clock arithmetic is what we tend to call it. But our field axioms, so the first one they mention is just the associativity of addition. Okay, we can add in any order we want here like this, or group things in any order we wish, sorry. So it's not really, we didn't change order in one sense, we just grouped them differently. And on the left, we added A plus B first, and on the right, we added B plus C first. So in any field, there's a thing called addition. And as long as we're dealing with stuff like integers, ZP is a finite set of integers that we'll see. Integers just add like they always have. We know how to add them. And then similarly, multiplication, we can regroup there. We can do this this way with multiplication. So associativity of both addition and multiplication. And again, we know how to multiply integers, so not a big deal there. Then we get the commutativity, right? Oops, that's a 3. A plus B is the same as B plus A, not a big deal there. And the same thing for multiplication. We can do that in either order, not a big deal. And we're all used to that. And then now, every field has a 0 element. We typically will call it 0. And so what we have is 0 plus anything is just that thing. Okay. And of course, we could turn that around and make it a plus 0 because of rule 3 there, or property 3. Okay, so we've got these five of the 10 axioms they give us. Well, similarly, there's this thing called 1 that's a multiplicative identity. So 0 is an additive identity, 1 is a multiplicative identity. And so we just get back our element A there, and again, we could multiply on either side by 1. 7, additive inverse. Now, this is where you have to be a little careful, is so there's this element called negative A, and if we add negative A to A, we get 0, and so our field has to have that. You want to be a little bit careful about immediately going to subtraction, okay? So this isn't subtraction. Now you can try doing something like that, saying that if we want A minus B, that is defined as A plus a negative B, or the additive inverse of B, okay? But notice this is an element named negative A, and it may or may not have a negative sign on it, but the point is that if we add these two things together, we get 0. And similarly, we have a multiplicative inverse. And again, so I have A times A inverse, I get 1. And once again, that's different possibly than talking about something like a fraction or division, right? You know, so we may not know what this means, okay? So we may not be able to quite do things this way. We're talking multiplication here. We haven't done a division. It's just that there is some element that if we multiply a times that element, we get 1. And so we'll call that the multiplicative inverse. And every element has to have a multiplicative inverse except for 0. And then 9, we have the distributive property. Okay, so we get AB plus AC there. And finally 10, 0 and 1 are not the same element. Okay, so those are our field axioms. And again, all except probably 7 and 9, 7 and 8, not 9, 7 and 8, they're the only ones that I think are a little bit different because you haven't really come up through all your arithmetic really harping on this idea of an additive inverse. We've just done things like subtraction and multiplicative inverse. I mean, these are things you know about. You've used the notation and so forth, but they aren't really pushed a lot. They aren't the main kind of way we talk about stuff. Now, so let's get back to these ZPs. P is prime. And the idea here is, you know, let's go with something like they use Z7 in the book. And so it has elements of 0, 1, 2, 3, 4, 5, and 6. Okay, so there are 7 elements there, but we start with 0. And the way we do this is we use this thing called a modulus, modular arithmetic, or looking at the modulus. So modular arithmetic. Okay, so the idea is this is a clock. And so one way to look at it is, you know, if we put 0, 1, 2, 3, 4, 5, and 6, if I were to ask you, you know, something like, what's 4 plus 5, right? If we think of the clock, right, you would go here to 4 and then add 5 more. So there's 1, 2, 3, 4, 5 more. I would get 2. Now, but as you can imagine, that could get kind of tough to do in general. We do have a definition, and that is that can help us a bit here. And we say, okay, so if I take some number A mod P like that, if I write that, this is the remainder of dividing A by P. And so, you know, if A is equal to some B times P plus R, where R has to be greater than or equal to 0, or strictly less than P for our remainder, then what we get is that A mod P is equal to R. Okay, and so we can kind of use that as our arithmetic. So for instance, you know, now actually they're using, I should go back here with the 4 plus 5 and put a circle around that. So if we say 4 plus 5, which is 4 plus 5, regular 4 plus 5, and then mod 7, that's equal to 9 mod 7, which is equal to 2, since 9 is equal to 1 times 7 plus 2. Okay, now we can do arithmetic, multiplication the same sort of way. Say I had 4 times 5. Well, that would be 4 times 5 mod 7, and so that's 20 mod 7, and that is equal to 6, since 20 is equal to 2 times 7 plus 6. Okay, and one can use, can talk about negative numbers and so forth. What would negative 3, if I want to talk about that, mod 7 be? Well, I can write negative 3 as I need a whole number, right? So something like negative 1, whole number, sorry, I really shouldn't say that, I need an integer. Negative 1 times 7, and then plus 4 gives me negative 3. And so, whoops. Well, I shouldn't have written it that way, sorry. I'm going to write this is equal to 4, since, that's the way I was doing it before, negative 1 times 7 plus 4 is equal to negative 3. Okay, so you get these funny things that see negative 3 mod 7 is 4. And so what does that mean? That means that 3 plus 4 must equal 0, okay, since 4 is the additive inverse of 3. Okay, so that negative 3, remember, that's the additive inverse. And sure enough, right, 3 plus, whoops, I need to put a circle around it. 3 plus 4 mod 7 is 0 because, right, since 3 plus 4 equals 7, which equals 1 times 7. Let me erase that a little bit there. There we go. 1 times 7 plus 0. So there's our remainder. Now, so to help you with this, you can make addition tables and multiplication tables. So here's 0, 1, 2, 3, 4, 5, 6. And you used to do these when you were much younger, and I hope you did anyway. And so 0 plus anything is that thing, so we know we've got that pattern. It doesn't matter which order we go in. Okay, and then 1 plus things, it just shifts it by 1, right? So this is 2, 3, 4, 5, 6, and 0. And then 3, 4, 5, 6, 0, and 1. And so forth. 4, 5, 6, 0, 1, 2, 5, 6, 0, 1, 2, 3, 6, 0, 1, 2, 3, 4, and 0, 1, 2, 3, 4, 5. And so now you can see these additive inverses here. All right, we've got additive inverses all along there, which means that we have going down here, -1 is equal to 6, -2 is equal to 5, right? The additive inverse of 2, and additive inverse of 3 is 4. Additive inverse of 4 is 3. Additive inverse of 5 is 2. And the additive inverse of 6 is 1. And we can see that from that. Similarly, we can do our multiplication table. And 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5. Whoops. Next page there. And 0 times anything is 0, so that's easy enough. So we put those in. And then 1 times anything is that thing. So 1, 2, 3, 4, 5, 6. So for any field, if you start with 0, 1, you're going to get this kind of a pattern to go here. And now it can start to get a bit more complicated, right? So 2 times 2 is 4, that's fine. 2 times 3 is 6, and 3 times 2 is 6. So that's going great. But now, 2 times 4 is 8. But 8 is 7 plus 1. And then 10 is 7 plus 3, and then 2 times 6 is 12, that's 7 plus 5. But now notice, right, we have all our numbers here. We've got 0, then 1, 2, 3, 4, 5, 6. And similarly, we can fill in this column because it should be the same as that row because it's commutativity. Now 3 times 3 is 9, so that gives us a 2. 12 gives us 5 again. And hopefully we get a 4 and a 1 out of these. 15, yep, that sort of has a remainder of 1 because 14 plus 1. And then 18, that gives us our 4. And so here's our 5, 1, and 4. 4 times 4 is 16, so that means that's a 2. 20, that's 14 plus 6. And 24 is 21 plus 3. And so 6 and 3. 5 times 5 is 25. Well, that's 21 plus 4. And 5 times 6 is 30. So that's 28 plus 2. And that's a 2. And then 6 times 6 is 36, which is 35 plus 1. So I was just finding multiples of 7. And notice, every, except for the 0 row and column, every row has 0 through 6. Every column has 0 through 6. And so we can also find our multiplicative inverses by finding the 1s. And so 1 inverse is 1. 2 inverse is equal to 4. 3 inverse is equal to 5. So 4 inverse is equal to 2. And 5 inverse is equal to 3. And notice here's a strange thing. 6 inverse is equal to 6. So not only is 1 its own multiplicative inverse, but so is 6. So there's kind of a weird thing. Okay, so that's something new that we aren't used to seeing. Okay, so that's our table of sevens. And, now suppose you had an equation that you wanted to solve, and so you have something like, suppose I've got 3x equals, and we need a number between, 0 and 6 here. And so let's go with 5. Okay, the way I would solve this is I need to multiply both sides by the multiplicative inverse of 3. And so that's 5. Well, so that gives me x equals, now the multiplicative inverse of 3 is 5, so that's 5 times 5. Okay, but that's modulo arithmetic. And so 5 times 5 is 25, or 21 plus 4, and so x is equal to 4. And so according to this, then x is equal to 4. We get 3 times 4 is 5. Let's go up and check that. Here's 3 up here, and 4, and 3 times 4 is indeed 5. Okay, so it's a little strange solving these equations. What if we have a system of equations? All right, so suppose I have something like x1 plus 2x2 plus x3 is equal to 4. And then how about we go with 2x1 plus 3x3 is equal to 6. Okay, and I wish to solve that. Well, so it works kind of that same way we did before, right? I just want to kind of take multiples of various rows, add them together to try to get rid of some things. And, well, let's add one more row in here just for the heck of it. And let's do x1 plus x2 plus 4x3 equals 2. Okay, so we'll have that. Now, so what I could do is, here I've got x1 and x3, so, what if I just get rid of, say, this x2 down here by multiplying everything through here by 2. So I'm going to take 2 times this bottom equation. Well, actually, better yet, instead of 2, what is the additive inverse of 2? All right, I have to come back up here. The additive inverse of 2 is 5. So actually, let's do that. I'm going to multiply that bottom row by 5. And that will give me the system of equations. x1 plus 2x2 plus x3 equals 4. I have 2x1 plus 3x3 is equal to 6. And now multiplying through by 5, I get 5x1 plus 5x2 plus, now 5 times 4 is 20, but that's 14 plus 6, so that's 6x3 equals, and 5 times 2 is 10, which is 7 plus 3, so I get a 3. Now, if I add equation 1 here to equation 3, if I add those two together, and put that back in the bottom, I have x1 plus 2x2 plus x3 equals 4. I have 2x1 plus 3x3 equals 6. Now, when I add these two, I get a 6x1. Oops, 6x1. Now I get 7x2, but that's 0. And then, oh, I get 7x3, which is also a 0. Oh, and wow, and I get 7 here. I didn't try to do that. I just kind of made up some numbers. Okay, but I get 0. And so that tells me x1 equals 0. Oh, but now if x1 equals 0, that means I have that 2x2 plus x3 equals 4. And I have 3x3 equals 6. Oh, well, I can solve that for x3. So that means that x3 is equal to 3 inverse times 6. Now, what was the multiplicative inverse of 3 again? That was 5. So this is equal to 5 times, better use that notation. I know I'm doing modular arithmetic, but you know, if I forget to do that, and actually, now that I think about it, I really should have back here put circles around all these plus signs, because I want to make sure I tell the reader that I'm doing modular arithmetic. And so I apologize I didn't do that in the beginning, but you see I can definitely make mistakes myself. So x3 is 5 times 6 modulo 7. So x3 is equal to, well, that's 30, that's 28 plus 2. So we get a 2 here. So x3 is equal to 2. And if x3 is equal to 2, then I can, you know, go back here, and I have that 2 times 2, like that, and then plus x3. Oh wait, no, x3 was 2. Sorry, almost messed that up again. So it's 2x2, and then plus 2 is equal to 4. Well, I do the additive inverse of 2 to both sides. So 2x2 plus 2 plus the additive inverse of 2. And so 4, whoops, 4. Ah, boy. I don't do a lot of modular arithmetic. 4 plus negative 2, or the additive inverse of 2. Now, the additive inverse of 2 again was 5. And so on this side, we just have our 2x, 2. And on this side, we have 4 plus 5, which is 9, which is 7 plus 2. Now notice that does look like it works just like subtraction. We get a 2 there. And now I need to multiply by 2 inverse times 2, x2 equals 2 inverse times 2. Put that in there that way. Now, and 2 inverse times 2 is 1, so we get that x2 equals 1. And so our solution was that x1 was equal to 0, x2 was equal to 1, and x3 was equal to 2. Now, if you get fractions, something's very wrong. If you get numbers bigger than your prime number that you're working with, something's very wrong. And I have used these a little bit, not a lot. Dr. LaGrange and I actually, we have a paper that the first page is on display out in the hallway, where we used modulo 2, okay? So we used Z2, and so that would be A mod 2, and pretty much that's just zeros and ones, that's binary stuff. But we looked at polynomials and coefficients and so forth in mod 2, and we factored those in mod 2, and it turned out to be a great way to solve the problem. And so at times it comes in handy. Your text mentions coding theory a lot. Now with mod 2, it gets really kind of weird, right? Because about all I can have, a single equation doesn't look very interesting, right? If I say x equals 0, or I could write the equation x equals 1. That's it. Those are the only two equations I have in unknowns x, because the coefficient on x can only be a 0 or a 1. Well, 0 doesn't look very interesting, right? So then I could have something like x1 plus x2 plus x3 equals 1, say. And then I could also have that maybe x1 plus x2 is equal to 0. Okay, so solving something like this, again, in this case, there's really nothing to do. I can't multiply through by anything but 1. And so I can add, though, these two rows together, and I will get 1 x1 plus 1x1, but 1 plus 1 is 2. Well, it's mod 2, so I get 0. So I'll get 0 there. Well, and again, I should probably do that. And I'll get 0 again. And so here I will get my x3, and 1 plus 0 is 1. So x3 is equal to 1. And if x3 is equal to 1, then actually what happens is I get x1 plus x2 plus 1 is equal to 1. Now if I add the additive inverse of 1 to both sides, well, the additive inverse of 1 is 1, right? Negative 1 equals 1. Okay, why? Since 1 plus 1 mod 2 is equal to 0. And so I'll add 1 to both sides, and I'll get x1 plus x2 is equal to 0. And so what that means is that x1 is equal to the additive inverse of x2. X2 is arbitrary. Now, but arbitrary, how arbitrary can it be? Well, x2 could equal 0 or 1. And the additive inverse of 0 is 0, the additive inverse of 1 is 1. And so our solution is that x1 is the additive inverse of x2. X2 could equal 0 or 1, and x3 has to equal 1. Okay, and so there's this idea of modular arithmetic. We don't do a lot with it, but I do think it's a nice thing to see and to realize that we can do all this equation stuff with some sort of funky looking fields. All right, so there we go. There are field axioms and some application of using those field axioms.